Hey everybody, it's Ripley again, and we're back doing 2.5 limits involving infinity. Now, let me show you what this really means, just for giggles. Let's say that I take the limit as x goes to infinity of e to the x. All right. Now, this is a limit involving infinity because, well, I'm headed for infinity, right? Now, think about that. If I've got e to the x, I take off here, and I got my point 0, comma 1. That's always my mother point. And what happens as x goes to infinity? Well, e to the x goes to infinity. Look at that. Not only is the infinity part of the limit, but it's also the answer to the limit. So that's basically what we're going to deal with. We're going to deal with values that either go to infinity or have a limit that we're taking at infinity. Okay, now let's take, for example, the limit as x goes to infinity of 1 over x. Now, just intuitively speaking, if I let x get huge, I mean crazy big, you just remember, infinity, we can't even wrap our brains around what infinity really is as far as numbers that are just so monstrous, right? So if I let x get really, really huge, what's got to happen to 1 over x? Well, remember, limits don't concern themselves with what happens at infinity. We can't stand on infinity and say, hello, I've arrived, this is infinity. But so it suits itself perfectly to the idea of limit. If I get as close to infinity as I possibly can, which means just keep right on going, right? What's this thing going to get closer and closer and closer to? As x gets huge, 1 over x goes to 0. In fact, if I take the limit as x goes to infinity of 1 over x to the n, as long as n is positive, right? If it's negative, I'm in big trouble because then I end up flipping this over the fraction bar. This sucker's going to be 0 every time. Okay? Now, I want to make sure that you understand some real subtle differences in terms of notation. Let's look at the limit as x approaches 0 of 1 over x. All right? So we know what 1 over x looks like. It's one of our mother graphs. Horribly drawn. It looks, I got to figure out a better way to draw on this thing, but it is what it is. If I take the limit as x approaches 0, well, what's going on? I'm going to approach 0 from the left and from the right. Now, you might be tempted to say that it's either positive or negative infinity, but the problem is that it goes to different infinities. Okay? Now, that may make you crazy, but remember what we talked about? If I put my fingers on, one finger goes that way, the other finger goes that way. If they don't go to the same spot, guess what? My limit does not exist. Now, what happens if I take the limit as x goes to 0 of 1 over x squared? Now watch what happens. So 1 over x squared looks like this, right? So if I take my fingers and I put it on, look at that and look at that. Now, where do they go? Do they head to the same spot? Remember, they never have to get there. They never have to get there, which they clearly can't. They're both headed for infinity. So the limit as x goes to 0 of 1 over x squared is actually equal to positive infinity. We can say that. Now, the subtlety with this comes with the difference between does not exist and infinity. All right, we know that infinity doesn't exist. It's not a place on the real number line where I can stand and say, this is infinity. Okay, so in the place of infinity or negative infinity, we can write does not exist. However, does not exist does not imply, so does not exist does not imply infinity, either plus or negative. Infinity does imply, plus or minus infinity, implies does not exist. Okay? Now, let's come back over here real quick. Well, we'll keep it red. If I take the limit as x approaches 0 from the positive side of 1 over x, well, now that's this guy right here, right? This would be a positive infinity. If I take the limit as x approaches 0 from the negative side of 1 over x, that means I'm going this way. Guess what I get? I get negative infinity. All right? That's pretty cool. Now, the trick with infinities is don't panic, either when they're going into the limit or when you get a value for the limit. Just use your common sense, okay? Now, let's use both of these functions, all right? But 1 over x and 1 over x squared to come up with some real common sense guides in terms of what's going on. Now, What do we call x equals 0 in both of these functions? What do you remember this from Algebra 2? What do we call that? We call that a vertical asymptote. X equals 0 is a vertical asymptote. Asymptote. All right? Now, how did we do that back in Algebra 2? How did we determine? Remember, we had rational functions, r of x equal p of x over q of x, right? And what did we do to figure out vertical asymptotes? Well, we took q of x and we set it equal to 0, and then we factored and we checked for cancellation, and whatever was left over was a vertical asymptote. So if you remember, if I let r of x, I'm just using r of x because it's a rational function, of x minus 3 over x squared minus 4. I end up with x, whoops, I end up with, sorry guys, end up with x minus 3 on top. I end up with x minus 3 over x plus 2, x minus 2. So this implied that x equaled 2, x equaled negative 2 were vertical asymptotes. Remember that? Now I don't want you to abandon that common sense intuition. However, this starts to break down if I'm not talking about a rational function. Now what we have in its place is, oh, by the way, think about tangent. Remember tangent? Tangent's got a bunch of vertical asymptotes, doesn't it? Sorry, I just interrupted myself. I got a bunch of vertical asymptotes. Remember how this guy worked? We had vertical asymptotes at negative pi halves, 3 pi halves, etc., etc. And we didn't have this way to define it. We had to do it in a more intuitive sense. Well, guess what? Limits at infinity or involving infinity give us the ability to do that. So now we can let's do vertical asymptotes, redefined. So we'll do a redux, redefined. All right, now check it out. Think about how we could redefine a vertical asymptote in the context of a limit. It's very simple. If the limit as x approaches a of f of x equals infinity. All right, what does that mean? That means you've got some function, let's put it over here. You've got some function at x equals a where if I approach it from both sides, it's taken off and I get this vertical asymptote. Or the limit as x approaches a of f of x equals negative infinity. Same thing, right? That would just flip this guy over, right? So I'd have, here's a and here's my function. I have a vertical asymptote at x equals a. Now, but also I can have one-sided limits. If I have the limit as x approaches a from the positive side of f of x. Now, I'm going to get a little lazy here. Instead of rewriting positive infinity and negative infinity, if this guy equals plus or minus infinity, or if the limit as x approaches a from the negative side of f of x equals plus or minus infinity, guess what? All of these imply that I have a vertical asymptote at x equals a. That's powerful goodness. Now, why is that useful? Well, it frees us of the constraints of only being able to deal with rational functions or even really like numeric approximations for asymptotes like we had with tangent and with secant and all those good things. For example, if I take f of x equals the natural log of x, right? And I go to graph it. Well, I know if this is y equals ln x, and this is the point 1, 0, I always like to write my other points. If I take the limit as x approaches 0 from the positive side, I know as x gets closer and closer and closer to 0, the natural log of very, very small numbers is negative infinity. So I know that x equals 0 is a vertical asymptote. Now, natural log of x is not a rational function. So I can't use my clever little trick, my little algebraic trick that I used over here. And we know before we were constrained when we dealt with like the trigs. And think about what you could do with tangent to prove that you had vertical asymptotes at pi halves k. All right, so that's a really powerful tool.